Daniela Söllinger, from PLUS Salzburg, speaks about hydrated vanadium oxide, a promising cathode material for lithium-ion and sodium-ion batteries.
Good afternoon, everybody, and welcome to my presentation about hydrated vanadium oxide, a promising cathode material for lithium-ion and sodium-ion batteries. So why is it important to work on batteries? To answer this question, let's think about renewable energy sources, such as the sun. So the sun is a renewable energy source we can use free and independent. Sunlight can lighten the darkest forest, or also on summer holidays, we can cook our meal outside without a furnace. So indeed, the sun helps us to see, to feel, and to do things which makes our lives easier. But what happens when the sun does not shine? How can we use the energy at these times? We can store the energy efficiently in energy storage devices, such as batteries. So in principle, a battery converts chemical energy and electrical energy via chemical reaction. It consists of two electrodes, which are called anode and cathode. During the charge and discharge process, the electrons and ions will move from the anode to the cathode. On the cathode side, we can use either in the lab in research or also commercialized anode materials such as lithium, sodium, or graphite. And you can see that the specific capacity differs depending on the anode material we use. The specific capacity is the amount of charge that can be stored in a material. So the higher the specific capacity is, the more can be charged in the material. If you take a look now on the specific capacities in the cathode material, such as lithium cobalt oxide, lithium iron phosphate, and lithium mangan oxide, we see that the values here are much lower. Moreover, if you take a look on the specific capacity, which is already reached in practice or in the lab, we see that the values are much lower. So the bottleneck to reach a high specific capacity in a battery is the cathode material. Therefore, the community searches also for other cathode materials which have higher specific capacity and maybe also have lower costs and a lower toxicity compared to, for example, lithium cobalt oxide. One of these cathode materials is hydrated vanadium oxide. Hydrated vanadium oxide has a high specific capacity of around 380 mAh per gram. Why? Because hydrated vanadium oxide has vanadium inside. Vanadium is a transition metal and has oxidation states from +2 to +5, so it can really easily be reduced and oxidized. Furthermore, hydrated vanadium oxide has hydrogen inside the structure, so it has hydrogen bonds, which makes it more flexible, bless you, and therefore the intercalation of different ions is also improved compared to other cathode materials. And it has a nanofiber morphology, which is also beneficial for the electrode and electrolyte interface. However, if you take a look on the specific capacity, which is nowadays reached in the lab, you see there is also a big gap between the specific capacity which we could reach and which is already reached. And to improve this, we can do different modifications. And one of these modifications is the substitution with molybdenum. So you can just buy commercialized vanadium pentoxide, and then you can do a soft chemistry synthesis to first get substituted vanadium pentoxide, and afterwards you do a hydrothermal process, and then you will get substituted hydrated vanadium oxide. And if you take a look on this crystal structure, you will not only see that we have partially replaced these red atoms from the vanadium to the yellow ones, which is molybdenum, but also the crystal structure expanded a little bit. Why is this beneficial? Because also here the intercalation channels have increased, and this makes it easier for the ions to move inside and outside from the structure. And therefore we assume that we also have improved electrochemical properties. Before I show you some results on this modification, let's have a look on high-weighted vanadium oxide and lithium cobalt oxide. And if you take a look now on the chemical formula, you see that lithium cobalt oxide does already have lithium inside the structure, and high-weighted vanadium oxide does not. So you can do a chemical pre-intercalation, so you can introduce lithium ions inside the structure before the electrochemical measurements. The synthesis is done, just takes a few hours, and at the end you will need a furnace to get rid of the water and the isoprop, which you will need to wash, but otherwise it's really simple. So now we have modified our high-weighted vanadium oxide, and we can use it as cathode material in our battery system. We will therefore go to the glove box because I use lithium metal as anode material, and afterwards you see the electrochemical measurements. On the y-axis you see the specific capacity, so again this is the amount of charge that can be stored in the material, and on the x-axis you see the cycle numbers because you can charge and discharge the cell more often. And if you take a look now on the measurements, you see that the unmodified high-weighted vanadium oxide in black and compared to the pre-sodiated high-weighted vanadium oxide in green, and the unmodified, the substituted high-weighted vanadium oxide in blue, has around 20% higher specific capacities. So indeed, this is already an improvement. And what we can also do is combine the two different modifications, which leads to the pre-lithiated high-weighted vanadium oxide substituted with molybdenum, which leads to around 40% higher specific capacities compared to unmodified high-weighted vanadium oxide. This is already great. And some of you may now ask why we should just change the system. Why is it not possible to stay in the lithium system and try to improve the stability and use this in a battery system? Well, some of you may know that lithium is also listed as a critical material caused by the primary control of lithium reserves by a few countries such as Chile or Australia. And on the other hand, the demand of lithium, especially in batteries, which you can see here for the blue bars, has increased in the last years. And therefore, we need also alternatives to at least partially replace lithium as a main part in batteries, also to meet the demand in the future. So how can we find a good alternative? One can take a look on the electrochemical series. So for a battery, again, we have an anode and a cathode. And to reach high energy densities, you will need for the potentials of these two a huge difference. So for the anode material, the negative electrode, you will need a really low electrode potential. As you can see, lithium has one of the lowest ones. So we will just have to increase step by step the potential and then find another alternative. First, we have potassium. Potassium ions are around 2 times larger compared to the lithium ions. So this will lead to a more challenging intercalation mechanism doing the electrochemical measurements. And furthermore, if you take a look on the costs, also potassium is more costly compared to other metals. Therefore, let's have a look below. We have calcium. Calcium is just around 1.5 times larger compared to the lithium ions, but it's also double charged. And this will also lead again to challenges doing the electrochemical measurements. So we will try to find something which is also single charged compared to lithium. And here we have sodium. Sodium is around 1.5 times larger, the ion itself, compared to the lithium ion, and it is single charged, similar to lithium ions, which is the reason also most of the people use sodium as an alternative compared to a lithium ion system. So for the next measurements, I have also used a sodium metal instead of a lithium metal and an electrolyte where sodium salt was dissolved compared to the lithium salt. And if we do measurements with the system, we see that we have reached around 60 mAh per km for around 25 cycles. Okay, so the same game as before. We can do a chemical pre-intercalation, but this time with sodium ions and not with lithium ions. And in this case, we will see that we reach around 40% higher specific capacities for the pre-sodiated high-weighted vanadium oxide compared to the unmodified high-weighted vanadium oxide. However, if you take a look after 25 cycles, you see that the difference between the unmodified high-weighted vanadium oxide and the pre-sodiated one is just 20%. And this means that the stability is also getting lower in this system compared to the unmodified one, which is a property we do not want to have. If we compare this with the pre-lithiated high-weighted vanadium oxide system, we saw that pre-lithiated high-weighted vanadium oxide led to higher specific capacities and also to higher stabilities. So now we are looking for another modification to improve also now the stability and the specific capacity in a sodium-ion battery system. And to do this, we just added reduced graphene oxide. So we changed the morphology a little bit and we got graphene sheets inside our structure. Therefore, the fibers got more or better connected to each other, and also the electrolyte gets more connected to our system, which hopefully then should lead to improved electrochemical properties. And if we do measurements with this system, we see that we have around 30% higher specific capacities compared to unmodified high-weighted vanadium oxide, and also after 25 cycles, the difference getting higher, so this means that also the stability increased. So this is great. However, some of you may have also noticed that the specific capacity in the system is below 100 milliampere hours per gram. And compared to the system with the lithium-ion battery, they are around 4 times lower. So we are independent of the modification we do in the sodium-ion battery system, always lower compared to the lithium-ion battery system for high-weighted vanadium oxide. Again, the reason for this is, if we take a look on the crystal structure, we have here this yellow area. This yellow area is this intercalation channel. So this is the area where the ions can move inside and outside from the structure. And if you imagine such a lithium ion tries to intercalate into the structure, it's getting smoothly into the structure because it's really small, compared to the sodium ion, which will have more struggles and maybe we also will more interact with the vanadium sheets compared to it. Indeed, we also did Operando XRD measurements, so I will just show you a little bit of it. Through Operando XRD measurements, we are able to measure the structure simultaneously to the electrochemical charge and discharge process. And if you do that, you can see that during the discharge process, which is the first line here, we have also a contraction, so a decrease of the unit cell volume for the lithium intercalation compared to the sodium intercalation, where we have during the discharge process here an expansion of the unit cell volume. So also the intercalation mechanism is a little bit different between those two. So now, as I say, sodium-ion batteries will mostly lead to lower specific capacities compared to lithium-ion batteries. However, if we also take a look on the material costs, mainly sodium, because it has a higher abundancy, will have lower material costs compared to a lithium-ion battery, which is also one of the reasons it might be an alternative in the future. It also depends just on some criteria like the specific capacity, energy density, costs, availability, and the application itself. Maybe some of you have seen that an e-vehicle was established or produced a few months later with a sodium-ion battery. The costs are much lower compared to the lithium-ion battery, but of course the specific capacity and the energy density is lower. So you will need to charge the battery cell faster, but anyway, someone with a lower budget can now also buy such a vehicle in the future. So to conclude, I hope I could show you that high-weighted vanadium oxide is a promising cathode material for lithium-ion batteries and for sodium-ion batteries, that through different modifications, such as the morphology changing or also the substitution, we can improve the electrochemical properties, and also that, of course, sodium-ion batteries may lead to lower specific capacities, but also they have lower material costs and then therefore can be used in other applications in the future. With this, I'm at the end of my presentation. I would like to thank all the people at the university, my supervisor for giving me the opportunity to do research on batteries, I thank the community, of course, that I got the opportunity to give a talk today. And last but not least, thank you for listening.